Next, we will discuss the direct comparison test, which is one of the two comparison tests. The other one is called the limit comparison test. So, to get started, let's consider the following series. And the question again is to analyze its convergence, that is, answer the question whether it converges or diverges. And we're going to start from scratch. So the first step is we're going to ask ourselves if this is a geometric series or telescoping series, which it isn't, or p-series, which it also not. And the next step, we're going to set up the divergence test by finding the limit of the general term as n goes to infinity. And since the limit is equal to 0, we conclude that the test is inconclusive, meaning that we have to move on and perform a convergence test. And the only test that we know is the integral test, so we can totally try to set it up by introducing a function, and we can only perform this test if the function satisfies the three conditions. So that is it continuous? Yes. Is it always non-negative? Yes. And the last condition is it decreasing? If you graph this function, you'll be able to verify that it is decreasing, so it looks something like this. So the answer is yes. So according to the integral test, we can conclude that this series behaves exactly the same way as this integral, which is, you may think it's good news, but what is the problem with this particular integral? Well, this particular integral is known for not having an easy antiderivative that can be written in closed form. So in other words, even though we do know how to set up this problem, we don't know how to integrate this. So it seems like the only test that we had doesn't work. So what else can we do with this particular series? Well, we can consider the following argument. Let's observe a few things. And the first thing we want to observe is that this series, by the way it is written, is definitely less than 1 over n to the power of 4. Why is it so? Because on the left side, we have this extra plus 1 in the denominator, which makes the denominator larger, which makes the overall ratio smaller. So this inequality holds. And what does that mean? That means that we now have compared our original series with another series about which we actually know quite a bit. The new series that we have written is actually p-series, and the p-value is 4, and 4 is greater than 1. And what does it mean to have a p in a p-series that is greater than 1? That means that p-series converges. And converges means it has a some finite limit. So if we now focus on our original series, we observe the following. It is between 0 and some number. So the full argument looks somewhat like this. So if you consider the series of partial sums, it is clearly bounded. Why? Well, because it is less than the limit of this p-series by which the original series is bounded. And since all the elements of this series are positive, that means this sequence of partial sums is increasing. Well, what does that mean? Well, by the theorem, we can conclude that the sequence of partial sums converges. But remember, the series converges if the sequence of partial sums converges. So the final conclusion is that this series converges, and this argument is called the direct comparison test. Now, the direct comparison test can be also used to show the divergence of a series. And let's consider another example. And just like before, we're going to run through the basic checks. Is this geometric? No. Is it telescoping? I don't recognize it as a telescoping. Is it p-series? The answer is also no. So if we run the divergence test, what's going to happen? The limit of the nth term as n goes to infinity will be equal to 0. So that means the test is inconclusive. And now, instead of trying to do the integral test, we're just going to jump right into the following argument. We can easily observe that this original series is actually greater than this series. So if I remove that -1 from the denominator, that will make the denominator bigger, and therefore the overall ratio smaller. So the right-hand side is diverging. It's less than the original series. And how do I know it diverges? Well, because it's p-series with p being equal to 1/2, which is less than or equal to 1, meaning that this series diverges. So what does it mean for the original series? Well, the original series is now has to be bigger than the divergent series, but to diverge means that the sum is infinite. So being bigger than infinity means it diverges. And again, this type of argument is called the direct comparison test. All right, so to summarize this approach, let's write this out. So the direct comparison test works if you have the following relation between some series. So if you have, let's say, two positive series, and by positive I mean the terms are positive, so each of these terms is greater than or equal to 0. And the following is true. So term by term, the one series is bigger than the other series starting at some value k, right? So again, it doesn't matter what happens for the first finitely many k terms. It only matters what happens for the infinitely many remaining terms. So if the following relation holds starting at some value k, then we can draw the following conclusions. If the largest series converges, then the smaller one also converges. And it kind of makes sense because if the smaller one is smaller than some number, but it increases, then it will satisfy the conditions of the theorem. It is bounded and monotone, therefore it must converge. So the smaller of the two will converge if the larger one converges, and on the other hand, if the smaller one diverges, it will push the bigger one to diverge as well. So the direction is really, really important here. You have to make sure that the larger one converges in order to conclude that the smaller one converges, and you have to make sure that the smaller one diverges in order to conclude that the larger one diverges. So let's go ahead and do a couple examples. Let's consider the following series. And as always, I'm going to start from scratch. Is this geometric series? No. Is this telescoping series? No. Is this P series? The answer is also no. Let's set up the divergence test. You never want to miss out on this one. So even though it may be time consuming, you still should set it up. In this case, the denominator goes to infinity, so the ratio of 1 over infinity goes to 0, so the test is inconclusive. And step 3, we're gonna try to do the direct comparison test here. And in order for us to do that, we have to find the relationship. So eventually you will develop intuition from seeing many examples and trying them yourself. For right now, I'm just going to tell you what the pattern here is. So this is clearly positive, and it's clearly bounded by this series. How so? Because the denominator on the right is smaller, therefore the overall ratio is bigger. But what's nice about this series is that this is geometric, and geometric series converge when the common ratio is less than 1. So make sure you don't get mixed up the condition for the geometric and the P series. So this one converges because it's a geometric series, and therefore the original series converges by the direct comparison test. Let's try another example. Let's analyze this series. And if we do it from scratch, we're going to try to recognize the pattern. Is this geometric? No. Is it telescoping? Probably no. Is this P series? Also no. let's set up the divergence test as a limit. We see that this goes to 0, so the test is inconclusive. And now we're gonna run some tests, and what I'm noticing here is that this series is actually greater than this series. How so? Well, the reason why this series is greater than the original series, I'm sorry, the series on the right is less than the original series, is because of this relation. ln of n always makes n smaller. So ln of n is always less than n. And if you take reciprocal of this, you're going to get the inequality flipped. How so? Well, just give it a try. 2 is less than 3, but 1/2 is greater than 1/3. So this inequality should make sense, but what do we know about the series on the right side? It is harmonic, or it's a p-series with p equals to 1. And what do we know about this series? We know that it diverges. So what does that mean in the context of the original question? That means the original series also diverges, and this way of argument is called the direct comparison test. So the conclusion is diverges by the direct comparison test. So we learned one of the two comparison tests called the direct comparison test.